Yeah, I can speak loud. Oh, okay, fine. Thank you very much. So, thank you very much for being here and for having me here. I'm really excited. This talk is going to be in deep learning, introduction to deep learning, and we're going to see some examples in Python in particular, because Python is nowadays the de facto language used in these kind of things, and I want to do it in a sort of unconventional way, as Nicola said, and I'm going to explain you very soon what's my idea of unconventionality. So this is something very unconventional. I have put some jokes in the slide, so if you don't mind. This is very unconventional. This is sort of gives you the idea of what I have in mind. I will use these as a sort of metaphor to introduce you to deep learning. I don't know if you know what this is, but I give you a hint about it. It's related to Doctor Who. I know if you see Doctor Who, if you're from Great Britain especially, you should know, but I will explain it. Anyway, so this is the conventional introduction. We talked a lot about deep learning today, and we've said many, many times that nowadays in some tasks, deep learning is also able to overtake humans in some specific tasks, such as object recognition and image classifications, for instance. And this is something that advertise the deep learning, typically. Deep learning is somewhat related to is about neural networks, and neural networks is somewhat related to human brains. So in more specifically, you can say that neural networks is a sort of discrete approximation of the human brain. And this is an example of neural network. And if you, at a glance, and if you want to describe it using some more specific terms about it, you can say that this is a multi-layer feed-forward neural network. I'm sorry about that. You can say that it's a multi-layer feed-forward neural network that starts with some input layer on the very left and followed by fully connected layers. Maybe it's not working. Is it? Right, sorry. Which is followed by multiple hidden layers in the middle and with non-linear transformation. If you quite new to these kind of things, maybe this is your reaction, right? Because you don't really know what I'm talking about. And so typically when you talk about deep learning, you have to learn, and you have to get used to these kind of terms and learn these technicalities. In the very end, when you talk about deep learning, you talk about neural networks. And neural networks are, in a very simple terms, a collection of layers. But what are these layers? So basically layers are, you have the input layer on the very left, then you have the hidden layer, you have all the possible connections between the layer, and you finally end up having the output. And you stack multiple layers one after the other. In one single layer, what happens is that you have the multiplication of the input. You call it neurons because you're neuron stuff. So you have neurons, and you connect every single neurons to elements in the next layer. So you call it weighted connection, and then you have the bias in the end. And so this is a linear transformation, quite simple linear algebra. And then you have some non-linear operation. This is called activation. You may have ReLU, for instance, sigmoid function, tan H, hyperbolic tangent, stuff like that. So you combine this linear operation plus non-linear activation, and this is one thing called layer. And you repeat these operations for each of these layers once you reach the output to get the final prediction. This is an overview at a glance of what a neural network is indeed. So for instance, if you take a look at this image classification task, the input layer is composed by pixels of images. You stack multiple layers, and then you have in the final activation layer the softmax classifier that basically tells you what's the probability of having the input image to different classes you have. For instance, in this case, you pass the image, and the network says, okay, the probability of being a bananas is 0.9. So in summary, a neural network is built of layers. Layers are matrix multiplication, then add bias, then some nonlinear transformation, and you repeat this computation layer by layer. And What the learning actually involves is learning the values of W and B, so weights and bias. And you have to do this repeating for each layer, and you do that by using a specific technique which is called backpropagation. If you won't have the details about that, so basically this is the idea. So apart from the awful math there, you basically have a sort of error function that calculates the loss, and you want to minimize the loss of the real data, the real target you have, so the real class of the image, for instance, and what you predicted. And then, so you start, this is called backpropagation, because once you go from left to right, passing the input directly to the prediction, so left to right, you do basically the opposite, moving right to left, correcting the values of weights using this backpropagation technique, which is basically based on optimizing the loss function and all the different weights by following the opposite direction of the gradient and blah, blah, blah. Right, fine, fair enough. Deep network come in different flavors. Today we've reached lots of examples. You may have feed-forward network, so the fully connected ones. You may also have convolutional neural network, the ones involved in image classification typically. Then you have a recurrent neural network. We have talked about sequence-to-sequence networks, for instance, or LSTM, long short-term memory. And then you have also cases in which you want to use, and that's only for supervised learning. It's typically used for supervised learning. You can also have unsupervised learning using deep learning. You can have autoencoders, you can have deep belief nets, and all the stuff. So if you want to join this field of machine learning, because deep learning is no more than a very narrow part of machine learning, you have to get used to all these kind of things. And I know that maybe it's still overwhelming to know everything from the very start, from scratch. So that's why I'm saying that if you know Doctor Who, you can say that deep learning is quite like the TARDIS. It's bigger on the inside, in the sense that once you get into the details, you have to learn lots and lots of things, and you have to get used to it very soon if you want to be productive. But anyway, what about Python? I promised you Python. So there are lots of tools nowadays, and as Irina already said, lots of frameworks changing every time. So we cannot advocate this one better than the other. I can only say what people use nowadays and what people used basically 6 months ago, which may be different. I promise you it's different. So anyway, in this picture, I just collected some machine and deep learning tools in the Python ecosystem. You have Shogun, PyTorch, Keras and TensorFlow, scikit-learn, PyML, lots of them. So the very first question you may ask yourself is, are all the same? Of course, the answer is no. If you take a look at only these libraries, PyBrain, PyML, scikit-learn. Scikit-learn is, for instance, the standard library to do machine learning in Python. All right, but scikit-learn is not used in deep learning world, and the reason why is that it lacks completely support for GPU computing. All right, when you hear about deep learning, you typically talk about GPU computing. All right, so most of the time, deep learning and GPU computing are somewhat related, and the reason why they're related, and so that's why these libraries are actually actively used and developed for deep learning instead of plain machine learning, because they have support for GPU computing. And that's the most important part of my sort of unconventional introduction. I want to tell you why GPU is so related to deep learning. One thing I want you to know, anyway, is that deep learning is no different from machine learning. The difference relies only in the learning models and techniques you use to do the learning. But in general, you can do machine learning also using these libraries. All right. The hardware related to deep learning is the GPU. When we talk about GPU nowadays, we talk about NVIDIA GPUs. There's something, we can discuss about it later, but so far when we talk about GPUs, we talk about NVIDIA GPUs. And the reason why it's used is because it has a better matrix algebra, it has support for parallel calculations, and that's one of the main reasons you want to use GPUs, and it's much more powerful. If you take a look at the schematics of the GPU, this is the NVIDIA Quadro FX GPU. You see that on a GPU, first of all, you have many, many more cores than you have on a CPU. And you also have high-speed memory on the GPU. If you go into more details, actually, there are some problems because when you do the calculation, there is this overhead of moving data around because you start creating objects in the main memory and then you want to pass these objects to the memory of the GPU, and these happens using, unfortunately you probably cannot read it, but the DMA transfer in the upper left corner is based on PCI Express, which is a bus, a physical hardware, a physical wire on the main board of your computer. And that's where basically data are transferred from CPU to GPU, so from main memory to the GPU memory, all right? And so you may optimize a lot this. There are actually projects related to this optimization because this is actually the real bottleneck when you do the computation. But once you have everything on the GPU memory, it goes very, very fast with respect to the CPU. And I give you an example about that. So take a look at this. This is VGG16. Irene already introduced it. That's a quite popular network, big network, the one winning one of the ImageNet competition. This is called VGG16 because VGG is the acronym of the Oxford lab invented it, and 16 is because it's composed by 16 layer. And if you want to represent it in a sort of vanilla schematic, this is what you have in the bottom of the slide. So you have convolutional blocks, apart from max pooling, dropout, and stuff like that, sorry. And in the final part, you have fully connected blocks and the softmax function as prediction in the end. All right? It's fine here? All right. So if you want to compare the percentage of time required for computation in a VGG network, and you have GPU forward time distribution, so this is just for forward pass, GPU and CPU, you end up realizing that as for the CPU on the right-hand side, the percentage of time spent in computation is more or less equal to all the different blocks. On the GPU, you can see that some blocks, especially the fully connected ones, are very, very fast, and most of the computation is spent for the convolutional part. If you compare the forward and the backward pass, you see lots of difference, especially when you compare GPU and CPU. They're basically totally different times. And so if you take a look at these times, you realize why you want to have GPUs. And of course, I'm talking about training time, right? Not inference. If you're interested in the inference time, that's a different story, because there you can indeed use also CPU, and that's why you may have these kind of network running on mobile devices, for instance, as we said this morning. But this is for training, and you see there's totally different order of magnitudes in the times you have on GPU and CPU. In the very end, when you do deep learning, you end up doing linear algebra matrix multiplication. In the back end, there is this popular function. This is popular because it's back from the 70s and numerical computation. This is called GEM. That stands for generalized matrix to matrix multiplication. And that's the heart of deep learning, I may say. So the difference is in the scale. If you take a look at the number of parameters you have, for just one layer, considering our example, you end up having 57 million parameters. and just for one, considering a batch size, so a batch size means that you pass to the network 256 images at a time, and you want to just compute the calculation for the very first layer, you end up having 50, if you do the math and the calculation, you have 57 million of parameters, and just for one layer, and then you have to repeat it for all the different layers. So I want to explain you why GEM is an art of deep learning, and the general idea I want to give you is that if you take a look at deep learning, in the very end, it's a lot of matrix multiplication. And that's why you want to have GPUs running, because you have more cores running there. Matrix multiplication, it's a highly parallelizable operation. So the more cores you have, the more efficient you are. If you take a look at fully connected layer, in terms of matrix multiplication and GEM operations, it's quite easy to understand, because you have input layer, the weights, and that's a trivial matrix multiplication. That's it. That's why on GPU it's very fast. If you take a look at convolutional layer in these terms, convolutional is a bit more complex operation if you want. So if you images typically are seen as cubes, because you have height, weight, width, and channels, right? Because you have RGB, for instance, encoding. So you have a three-dimensional object, and you want to do this convolutional kernel, which is this cube. And the idea is that you want to apply this cube in every single part of the image, and then you want to get your output. So in terms of operation, this is what you do when you do convolution, basically. So you have this green square, which is called the kernel or the filter, call it whatever you want, however you want. And then you pass this filter through the image, and then you get the output. As you see in the animation, I cannot move too close. Maybe I move here. All right, fine. So, sorry about that. And that's the output of convolution. So, to be honest, the way convolution is really implemented is this way. So instead of having this image, this kernel moving around the image, the real implementation of convolution is creating this very big matrix, having the different weights of the kernel, and you call it C, and in the very end, you do the convolution by doing, again, matrix multiplication. So you have image multiplied by this C matrix, and you calculate the convolution, and this is the way you want to implement really convolution, because it's very easy to create the transpose convolution, which is the opposite function, and this is super efficient and very efficient because it relies on GEM again, and it's matrix multiplication again. So we talk about lots of these deep learning frameworks. What's the difference among these? Because they're not the same ones. You have many, many options and many, many reasons why you want to use one instead of another one. So one difference is in the way you specify the different models. You have configuration files, for instance, Cafe is one. Or you may have a programmatic way to generate your model. That's the case of PyTorch and TensorFlow, for instance. Another difference is that you can think of a neural network as a graph, and that's a central concept. And you may have these, if you think of network as a graph, you understand that you may have this graph as a dynamic graph or a static graph. I will tell you in a very shortly what's the difference. PyTorch, for instance, and Chainer are the two considering the dynamic graph computation. Static graph computation is Theano, TensorFlow, for instance. So comparing the two, Theano and TensorFlow, Theano is a deep learning library with Python wrapper. TensorFlow is a deep learning library recently open sourced by Google. They're similar in the sense that they both are based on static graph definition. To be honest, TensorFlow strongly got inspiration from Theano. but they're different in the sense that TensorFlow has been has better support for distributed system. Since TensorFlow is actually a Google product, it has been thought from the very beginning as a tool to do distributed computation. That's one thing that strongly differs the two. And TensorFlow has nowadays a larger community, and that's why TensorFlow is nowadays considered as the core tool for deep learning. If you compare TensorFlow and PyTorch, which is becoming more and more popular nowadays, PyTorch is a deep learning library providing maximum flexibility and speed. And this is very interesting. I think I don't have the time to explain in the very details the difference between the two, but I will really happy to discuss about that in the question time. General is that TensorFlow is based on static graph computation, as we said. It has a sort of TensorFlow API, and it has a static compilation and distributed support, and there's this killer application. I will show you some examples, which is called TensorBoard, which is a great visualization tool for your experiments, your neural network experiments. On the other side, Torch and TorchNN is based on differently on, yes. Yeah, no problem. Yep, all right. So, Torch is based on dynamic graph definition. It has a NumPy-based API, so the API is more intuitive with respect to TensorFlow. And in fact, sometimes it's called NumPy with GPU support. And it's JIT compiled. That's one great feature that makes the difference with TensorFlow that has static computation. So let's give a focus on TensorFlow now. I will give you just the idea on what does it mean to work with TensorFlow. So TensorFlow, as other frameworks in these sets of tools, provides you support for tensor computation. So what actually is a tensor? Formally, a tensor is a multilinear maps from vector space to real numbers. So a scalar is a tensor. A matrix is a tensor, vector is a tensor. But if you talk to a mathematician, math guy, or basically they may argue that a tensor is not just like any multidimensional thing, right? But we can say that an intuitive way to represent a tensor is a multidimensional array. So when we now speak about tensors, we're considering multidimensional arrays, right? So if we want to have a comparison, I don't know if you're into NumPy, but if you want to do a comparison of the APIs between NumPy and TensorFlow, in case you don't know, NumPy is the standard Pythonic numerical library. So if you want to do numerical computation in Python running on CPU with no distributed support, you can have NumPy, and you must use NumPy. So if you take a look at the similarities and differences of the API, for instance, if you want to create a multidimensional array in NumPy of zeros, 2 times 2, that's the API, which is exactly the same one in TensorFlow. If you want to do sum in NumPy, you have to call it reduce sum. So as I told you, it's a sort of NumPy-ish API. It's not very equal to NumPy, but it's sort of. You have shape on NumPy side, you have get shape on TensorFlow side, so on and so forth. Maybe one that is relevant is the dot product. You have dot function on NumPy, and you have matmul for some reason in TensorFlow, but that's exactly the same operation. So one very difference from TensorFlow and NumPy is that TensorFlow requires explicit evaluation. And so far, if you take a look at the API, they basically look very similar. So maybe if you're not very into it, you're not getting why you want to use TensorFlow instead of using NumPy, for instance, apart from the GPU. Well, if you do this, if you import NumPy and TensorFlow, and you create this 2 times 2 matrix of zeros, and you want to print it in NumPy, this is just Python and NumPy, this is what you get, right? Expected, no problem.
If we want to do the same with the same API in TensorFlow and you want to print it, this is instead what you get. This is just a tensor object of that shape with no value in it yet. Because TensorFlow requires what is called explicit evaluation. So you have to evaluate the tensor object and then you get the value. This is because TensorFlow is based on this idea that a machine learning algorithm may be represented as a complex graph of operations. You have this graph which is called data flow graph. In this graph, each node represents an operation, so a matrix addition, matrix multiplication, whatever you want. And each edge is a multidimensional tensor, is a multidimensional data set represented as a tensor, on which these operations are performed. In more details, nodes are instantiation of an operation with a number of inputs which is equal or greater than 2, and the output must be greater than or equal to 0. And edges may be divided into categories. You have data edges, so tensors carrying actual data, and dependency edges, so edges controlling the dependencies of the operation, right? So the internal representation of all the operations applied on the machine learning algorithm in TensorFlow is basically represented as a graph of operations. This is an example of sets of operations for logistic regression. I will show you in more details this in the next slides. But if you want to implement a multi-layer network, basically you have to repeat this set of operations for each set of layers, and the graph is in charge of taking the connections from one edge, from one layer to the next one. And so repeat every single process here. So, right, yeah, sorry. So let's implement, yeah, I can make it, I promise. So let's implement a logistic neuron using TensorFlow API. Yep. And we're going to use quite popular MNIST dataset, so image of handwritten digits. Right. So that's the example. So we're gonna through this in different steps. So we import TensorFlow, we create this placeholder object. The placeholder object gives you the idea that basically tensors are just placeholders. So objects where you want to structure the data you're expecting to process, but you're not passing the data yet until you really feed the graph. So you create X and Y. X is the data, Y is the prediction. So X is going to be a placeholder of floating point numbers of that dimension. So none means any number you want. So it's this is called batch size, so the number of samples you want to provide to the network every time. And 784 is just the number of features you want to use in this case. So it's 28 times 28. Y is the floating point placeholder for 10 classes, and that's because it's for we have digits from 0 to 9. That's our problem. Then we create this model scope. So I just organize this code in different scopes. I will give you an idea very soon why. Do you want to do that in TensorFlow? So we create the variables for W and B, which are actually the learning parameters, what we want to learn during the learning process. So the values of weights and the values of the bias. By the way, logistic neuron is just logistic regression, all right? So what we're actually doing now is to implement a very simple logistic regression model using a neural network. And despite the name, logistic regression is just for classification, right? Then after that, we create an activation function, so the real classification in this case, because we're going to have just one layer. And so we have the softmax applied to the sigmoid function of the matrix multiplication, so x times w plus b. So that's the logistic function, and in the very end, the softmax to classify the output. We then add this instructions, these are the summary operation, and we're telling TensorFlow that during this computation, it must collect information about calculating the histogram of the weights and the bias, and have to take the log of all the scalar operation for the mean weights and the mean bias. So these are information that will be included in a very interactive log you have in TensorFlow, which is called TensorBoard. And if you have multiple layers in TensorFlow, you basically have to repeat these operations for each layer. Then you have the cost function you want to minimize. And so in this case, it's just cross entropy, and the cost is just this bunch of instructions. So we want to reduce, so we calculate the cost is the mean of the sum of all the cross entropy along the different indices of the tensor we have. And we want to minimize it. We create summary to monitor the cost function again to be visualized in the TensorBoard. And the final part is we create the scope for the training process. So after we created the model and the cost function, we specify the optimizer. In this case, it's gradient descent optimizer with some learning rate, and we want to minimize the cost. All right? That's the TensorFlow API. It's not very intuitive in the very beginning, but this is how you do it in TensorFlow. And finally, the metric we want to compute during the learning process. So in this case, it's just accuracy, and we want to calculate the accuracy during the learning process. And we want TensorFlow to log the scalar value of each accuracy score calculated during the training. All right, so we end up creating this summary writer. So we specify what is the graph we want to log and what's the path of the folder we want to store the logs. And so if you want to print the different summaries we collected during the model computation, the graph creation is this one. So we print all these summaries we have, and then we print all the basically this merge operation. So we can merge all the different summary in one single point. All right, and the fourth and last step to do the learning in pure TensorFlow is this. We create a session, and this is where the explicit evaluation model comes into play, because we create a new session where we pass the graph we created and we feed, in this session, data to this graph. All right? So we create a new session, we run it, and we implement the main loop for the learning process. So we repeat this operation for all the epochs we want, for the training epochs, and during each epoch, we basically feed the optimizer and the cost function and the actual data. So we actually feed the actual data to these tensors, and these tensors, so if you think of them as graphs, you actually get it, what's going on. If you every single tensor is connected to each other tensors. So once you feed data into one tensor, since this tensor is connected to each of the other operations, you basically end up, TensorFlow is in charge of get the data and pass these data through the different connections in this graph. All right? Okay, so, and this is, if we basically run it and we get this performance, so far so good. And this is just to implement a very logistic neuron, so it's a bit difficult in the very beginning. And if you take a look at, if you take a look at the TensorBoard, as I promised, TensorBoard this is how it looks like. And once you have run your session, TensorFlow automatically has gathered all this information and generates these charts for you. For instance, this is the charts of the scalars. So you have unfortunately you cannot read it, but this is for accuracy, and this is for the loss trend. This is the graph representation of what we implemented. So actually, this is what TensorFlow, this is how TensorFlow represents all the operations we've implemented. So this is the actual graph TensorFlow created. And these are the histograms for the cost function, for instance. And that's it for TensorFlow. I just want to give you a very quick overview to Keras, which is a nice library. I really like it. And I strongly suggest you to go for it, especially if you're quite new to this. Differently from TensorFlow, as you probably already guessed, Keras is quite tightly integrated with TensorFlow. Keras is a deep learning library, I typically said, for perfectionists with deadlines. That's because it's a higher level API for neural networks, which is written totally in Python. So if you're into Python, it's very easy to understand the code. And one of the main advantages of Keras is that Keras supports different backend. So you can actually have Keras running on top of TensorFlow, CNTK, Theano, and actually also MXNet. Keras allows you for fast prototyping, and the API is very user-friendly. Supports all the kind of networks you may want, and runs seamlessly on CPU and GPU. And is compatible with Python 2 and Python 3. And if you want to really understand why Keras is tightly integrated to TensorFlow, I can tell you that from now on, from release of 1.3 of TensorFlow, which is the actual stable release, you can do something like from tf, which is TensorFlow.contrib, import Keras. So actually, Keras is now inside TensorFlow. So if you install TensorFlow, you already get it. And from the next release of TensorFlow, you can actually have directly Keras integrated into TensorFlow. This means that you can access the friendliness of the API of Keras from TensorFlow, and at the same time, using the distributed support for distributed computation TensorFlow provides you. And in the very end, if you want to implement the exact same logistic neuron using Keras, that's all your code you need. You just have to import Keras and some layers, dense layers and activation layers. You just create this sequential object. You add to this sequential object different layers you want. In this case, we want to have just a dense layer having 10 neurons in the output with that input shape and that activation and the softmax activation function in the very end. We compile the model using the optimizer. In that case, it's stochastic gradient descent, so the same one we use it. Categorical cross entropy was the loss function we want to specify, and then you fit the model. You don't have to implement anything from scratch, because if you want to do in pure TensorFlow, you end up implementing every time the same code. Keras is just an API, an higher level API that sits on top of TensorFlow and gives you the ability of having a very simple API to create networks. It's very easy to understand and very quick to use, even for newbies. If you want, that's it. So if you fit the model, basically this is what you get. So automatically you specify that you want 25 epochs, and then you run it. This is just for 10 epochs, but Keras provides you all the information you need. So the loss values changing during the different epochs, how much time does it take, so on and so forth. It's very, very easy to use. If you want to know more about that, I can just reference to this link. It's actually a Keras tutorials I end up making during many conferences. It's on my GitHub profile. So you will find Jupyter notebooks explaining you how you can actually use Keras to do these kind of things, and how Keras is highly integrated with TensorFlow. So for instance, operating through Keras with the tensor board, which is quite nice to have. And so that's it. This is all I have. And if you have any questions, we'll be happy to reply and answer. Thank you very much.